Okay, so this is the last problem in the PowerPoint for chapter 3. You uh, will just see on that last slide this pedigree without the genotypes written in there. And then I talked about it a little bit on the video, but you obviously couldn't quite see what was going on. So let's go over it here. And so on these pedigree problems, the question for this problem is, what's the probability of this child down here, the child of H and I, being affected with whatever it is that they're affected with? We'll just make it easy. We'll call it being a recessive. Well, we can see by the pedigree that it is a recessive allele, because you can see that E has two parents. Neither of the parents are albinos. We'll just make it easy and we'll call it albinism. And neither A nor B is albino, and they have E, which is albino. Here again, G has parents C and D, neither of which, both of which are wild type, and then G is albino. And so it's a recessive condition, okay? So here, we just write it all out. Big A dash, so big A or big A little a is wild type, and little a is an albino. I don't know why I put an A at the end there, but it's albino. Okay? So with these pedigrees, what we always want to do is we want to make it as simple as possible for ourselves. And we want to write down as much information, because we don't want to house that in our brains, because then we get overloaded and we get confused and we end up making mistakes. And so the best thing to do with these pedigrees is just to write down the genotypes that you know. Okay, so this E, it's written in pencil, so you can't see it very well, but it's little a, little a. So let's just go through and write down the genotype for E and G. They're both albinos, so we know that their genotypes are little a, little a. Each individual that has a, little a, right? Each albino has to have each of their parents have to at least be carriers, right? Both A and B have phenotypes that are wild types, so you know that they're both carriers. Neither of them are filled in, so neither of them are albino. So we know automatically that their genotypes are big A, little a. Down here with G, same thing. We know both of G's parents are big A, little a. Here, E is little a, little a. F, and this is with all of the pedigrees, unless there's information to the contrary, you assume, since these conditions are usually rare, carriers randomly picked from the population are usually rare, so we assume that they are not carriers unless there is evidence that suggests otherwise. Since both of these children, I and J, are both wild type, there's no evidence that F is a carrier. And so F is big A, E is little a, little a. When you pair up little a with big A, all of their offspring are going to be carriers, right? Because E is little a. And so we know that the genotype for I is big A, little a. The genotype for J is big A, little a. And those are all of the genotypes we know. So we basically know everybody's genotype except H here. Okay, so now in order for the child of H and I to be affected, we have to have a couple of different events happen. The first event, just like I was talking about before, for an individual to be little a, both of their parents have to at least be carriers. We know here that I is already a carrier, right? So the probability that I is a carrier is 1, because we already know that I is a carrier. But here we don't know if H is a carrier or not. So that's the one event that we have to calculate. We've got to figure out the probability for H being a carrier. Then we have to figure out the probability if both H and I are carriers. What is the probability that they have an affected child? So let's take this first one. So here I've set it up. P, H, C. So that's the probability that H is a carrier. And we can take the matings of C and D, right? Do a Punnett square form, big A, little a, mating with big A, little a. Here are all of the possible outcomes, right? Big A, big A, little a, little a, little a, big A, little a. And in order to figure out the probability, we have to say, okay, what's the probability that H is a carrier? So big A, little a here is a carrier, was an individual that's a carrier. Big A, little a here is an individual that's a carrier. So there's two chances, there's two outcomes that that individual is a carrier. Here, I've drawn a line through little a, and the reason I've done that is because little a is not a possible genotype for H. If H was little a, then this square would be filled in red. So we just take that out of our calculation. And so here, there are two different probabilities. There are two different genotypes it can be. H can be big A, or big A, little a. Here are the three different outcomes. Two of those three outcomes are big A, little a, or being a carrier. So the probability that H is a carrier is 2 over the total number of outcomes, 3. So 2/3 of a chance. Okay, so now let's say that H is now a carrier. Both H and I are carriers. What's the probability that they have a child, that's C here, that's affected? And so you just look at that Punnett square again, big A, little a, big A, little a. Of the 4 different squares, only one of the squares is an affected child, so that's 1 in 4. So that's the probability that the child is affected if both parents are carriers. And so for both of these events to occur, for H to be a carrier and for the child to be affected, whenever you hear and, you multiply. So you just multiply 2/3 times 1/4, and that gives you 2/12 or 1/6. And that's the answer to the problem.